Namaste dosto. Imagine you have a perfectly balanced coin in your hand. You toss it once. What are the chances it will land heads up? This simple question gives us the perfect starting point for today's topic, theoretical probability, or as some call it, classical probability. But what makes this theoretical idea so special? Well, it's all about assuming that every outcome is just as likely as any other, without even needing to do a real experiment. So, how do we find the probability of an event using this approach? Here's the magic formula. Probability of an event E, written as P of E, is the number of favorable outcomes divided by the total number of equally likely outcomes. In plain words, if an event can occur in F favorable ways out of N total outcomes, then P of E equals F divided by N. Let's take our coin toss example. Tossing a fair coin once gives us two possible outcomes, heads or tails. Since both are equally likely, the probability of getting a head is one favorable outcome over two total outcomes, which is 1/2. That means P of head is 1 divided by 2. To help you visualize this, think of a small tree diagram with two branches, one for heads and one for tails. Each branch is an outcome, equally likely to happen. No experiments needed here, just logical listing of all possibilities. Arey wah! Now you know how classical probability works, listing all possible outcomes and dividing the number of favorable ones by the total. Simple yet powerful. Moving forward, let's understand some important words that make probability easier to talk about. Experiment, sample space, and event. An experiment is any activity or process that we can repeat and observe outcomes from. For example, rolling a dice once is an experiment because it results in just one outcome. Now, the set of all possible outcomes of this experiment is called the sample space, written as S. When you roll a die once, S contains all the numbers you can get, 1, 2, 3, 4, 5, and 6. An event is a smaller group or subset taken from that sample space. Say, you want to find the probability of rolling an even number. The event E would be the set of outcomes 2, 4, and 6. So if the number of favorable outcomes F equals 3, and the total outcomes N equals 6, the probability P of E is 3 divided by 6, which simplifies to 1/2. Imagine seeing this on a Venn diagram. A big circle for the sample space S, and inside it, a smaller circle representing the event E for even numbers. This visual helps you understand how events fit inside the complete world of all outcomes. Excellent beta. Now you're comfortable with the building blocks of probability. Let's take a step deeper with some fundamental rules about probability, the axiomatic basis. Don't worry, it's simpler than it sounds. For any event E, there is something called its complement, written as E bar, which basically means not E. So if E is getting a head on a coin, E bar is getting a tail. A key rule here is P of E plus P of E bar is always equal to 1. This means the event either happens or it doesn't, covering all possibilities. Also remember, the value of any probability lies between 0 and 1. 0 means impossible event and 1 means a certain event. Think about it this way. If the probability of rain today is P of rain, then the probability of no rain is 1 minus P of rain. This complement idea is very useful when direct calculation is tricky. Just find the probability of the complement and subtract from 1. Picture a number line from 0 to 1, marking where different probabilities set. This helps you see that all probabilities neatly fit between these two ends. Shabash. These rules keep our probability calculations aligned with logic. Time for a quick solved example. Tossing a fair coin once. What do you think the chances of getting a head or a tail are? Let's see. First, the total number of possible outcomes, N, is 2, heads or tails. Favorable outcomes, F, for a head is 1. Using our formula, P of head equals 1 divided by 2. Next, for tails, instead of recounting, use the complement rule. P of tail equals 1 minus P of head, which is 1 minus 1/2, giving us 1/2 again. Step back and check. Probabilities add up. 1 half plus 1 half equals 1, meaning we've accounted for all possibilities. Visualize this again with a tree diagram showing two branches, one for head and one for tail. Arey vah! Such a simple example packs a lot of learning. Let's try another example. Rolling a fair 6-faced dice once. Can you guess the probability of getting an even number or an odd number? Here, total outcomes n equals 6 because the dice can show numbers from 1 to 6. The event even number includes 2, 4, and 6. So favorable outcomes F are 3. P of even equals 3 divided by 6 or 1 half. Similarly, the event odd number includes 1, 3, and 5. Also 3 favorable outcomes. P of odd equals 3 divided by 6, again 1 half. Check again. Adding P of even and P of odd gives 1. Perfect. Imagine a number line showing dice faces grouped as even and odd. This grouping helps quickly spot probabilities. Excellent beta. You're getting the hang of it. Ready for a card trick question? Suppose you pick one card randomly from a standard deck of 52 cards. What's the chance of drawing a heart or a red card? Total cards n equals 52. Hearts are 13 cards. So P of heart is 13 divided by 52, which simplifies to 1/4. Red cards include hearts and diamonds, together 26 cards. P of red equals 26 divided by 52, which is 1 half. The complement, not red cards, are clubs and spades, also 26 cards. So P of not red is 1 minus 1 half, again 1 half. All cards belong to exactly one suit and one color. So everything adds up perfectly to a total probability of 1. Picture this as a pie chart with suits in different colors. It really brings these numbers to life. Shabash. You're nailing classical probability. Now, here's a shortcut tip. Sometimes, it's easier to calculate the probability of not E, then subtract from 1 to find the probability of E. Why? Because counting the complement might be simpler. For example, what's the chance of getting at least one head when tossing two coins? Instead of listing every way to get a head, find the probability of no heads appearing. That means both tosses are tails. The total outcomes for two tosses are 4. HH, HT, ETH, and TT, each equally likely. Probability of TT is 1 divided by 4. So, probability of at least one head is 1 minus 1/4, which equals 3/4. Visualize this with a grid or matrix showing all 4 outcomes: HH, HT, ETH, and TT. These logical tricks save you time and avoid long counting. Let's wrap up what we've learned today. First, the fundamental formula. Probability of event E is favorable outcomes F divided by total outcomes N. Next, the complement rule. Probability of E plus probability of not E equals 1. Equivalently, probability of not E equals 1 minus probability of E. Also remember, probabilities always range from 0 to 1. Theoretical probability assumes all outcomes are equally likely and requires you to know the full sample space. Events are subsets of this sample space, so grasping the relation is key to calculations. Finally, using logical techniques like complements and symmetry can make problems much easier. Examples with coins, dice, and cards clearly show how these classical ideas work. Soch ke dekho. Probability helps us make sense of uncertain situations just like this. Keep practicing, shabash, and you'll master probability in no time.